energy formulation. P of xy equal to 1 by z pi I, that is pi of I, that is pi over I. This pi of xi comma yi pi over of I comma j psi of yi comma yj. Take logs drops z. E of x comma y summation over I pi of xi y comma yi plus summation over I comma j psi of yi comma yi. We call E an energy function. E an energy function. Named free from energy problems in statistical mechanics. Individual terms are potentials. Individual terms are potentials. Note, derived this way, its energy maximization. Be careful and check each formulation individually. Each formulation individually. Deliver this way, its energy maximization. Be careful and check each formulation individually. Energy formulation under E of xy equal to summation over I pi of xi xi comma yi plus summation over I comma j psi summation over ij psi of yi. Here x1 y1 x3 y3 x2 y2 x4 y4, that is x1 y1 x2 y2 is front and back y3 x3 y3 x4 y4. Here this pi, here x y, this psi here, this is y direction, this is y direction, this is x, okay, this is y. Here this y, here this xy, so here, okay. Unary potentials pi, local information about each pixel, how likely a pixel slash pitch belongs to a certain class. Pairwise potential psi, neighborhood information enforces consistency, how different a pixel is from its neighbor in appearance. CRF segmentation example. Boykov and Jelly in 2001 in paper, this paper. They are the author. Boykov and Jelly. E of xy equal to summation over I pi of xi yi plus summation over I comma j psi of y comma yi comma yi. Variables xi annotations input foreground, background empty. Binary variable yi is the binary variable, foreground, background. Unary term pi of xi comma yi equal to k of xi non equal to yi. Penalty for disregarding annotation. Pairwise term psi of yi comma yj equal to yi not equal to yj into wij. Encourage smooth annotations. Wij is affinity between pixels I and j. CRF segmentation example. Solving efficiently. Grid structured random fields. Max flow, min cut, optimal for binary labeling. Submodular energy functions. Boykov, Kolmogorov, and experimental comparison of min-cut max flow algorithms for energy minimization of vision in vision. PAMI 2004. Fully connected models, efficient solution with the convolution mean field, Crahanwell and Colton author, denoting efficient inference in fully connected CRFS with the Gaussian edge potentials, NIPS in 2000 paper. Paper name, year published, year 2011. Paper name, NIPS. Grab cut, interactive foreground extraction. Magic wand, Adobe 2002. User input. Intelligent scissors, Martinson and Barrett 1995 paper. This for cutting. Intelligent scissors. This is magic wand in Adobe 2002. Here grab cut. Grab cut is total. This is intelligent sensor. Intelligent scissors. Result here for this one, these regions available. This one removed. 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 Here, this one available. Boundary. Regions. Regions and boundary. Grab cut. Regions and this is the regions. This is the boundary. Here regions only. No, here boundary also here also. Because region means this one removed, this part removed, this part removed, no? Remaining only here, no? That one is the regions. Here removed some thing plus boundary also is there. Boundary, this one is the boundary. Region, full region. Inside all are regions. Crab cut formulation. E of x, comma y, comma theta, comma k equal to summation over I pi of xi, yi, theta, ki plus summation over ij psi of yi, yj, xi, xj. Variables xi equal to pixel. Xi is the pixel. Yi for all x 0, 1. Foreground, background label 0, 1. Ki for all 0, 0 to k minus 1. This is the GMM mixer component. This is the yi YA is the foreground background label 01. This 01. Okay, this 01. Here GMM mixer component KI. XI is the pixel. Theta is the GM model parameters. I equal to I is the Z1 to ZM. This is the RPG image. Unary term pi of xi, yi, theta, ki. Log of GMM probability pairwise term psi of yi, yj, xi, xj equal to comma of yi not equal to yj. Exponential of minus beta of mod of xi minus xj square double mod. Graph cut iterative optimization. Initialize mixer models based on user annotation. Assign GMM components KI equal to argument minimum pi of xi, yi, theta, ki. Learn GMM parameters. Theta equal to our argument minimum of summation over I of pi xi, yi, theta, ki. Estimate segmentation's minimum cut, min cut. Y equal to argument minimum E of x, y, theta, k. Repeated 2 to 4 until convergence. 2 to 4 until convergence. Until convergence. Graph cut results. Graph cut results. This is the graph cut. So result. This is the graph cut. In this image. Here. Here. Graph cut. Image. Further editing with the graph cut. This is the in this image automatic segmentation. Okay. Automatic segmentation. Then user interaction here. Okay. Then automatic segmentation also. Automatic segmentation. User interaction also this is available. Automatic segmentation also this is available. Summary: graph cuts with this CRFS pros very powerful, get global results by defining local interactions, very general, rather efficient, becoming more or less standard for many segmentation problems. Graph cut was 2004 cons only works for submodular energy functions, binary, only approximate algorithms work for multi-level case. Improving segmentation efficiency, images contain a lot of pixels. Image contains a lot of pixels. Even efficient methods can be slow. Efficient method can be slow. Efficiency trick, super pixels. Group together similar pixels. Cheap and local over segmentation. Must be high precision. Many methods exist. Try several. Another trick, resize the image. Do segmentation in lower reservation. Image compression. Once again, to recall basic. The goal of image compression is to reduce the amount of data required to represent a digital image. F of xy compress transmit channel, T compress F cap of xy. Then here storage device, then retrieve decompress here. The goal of image compression is to reduce the amount of data required to represent digital image. Then image compression already we have seen. continued lossless information preserving